Hi there guys, I'm Chris Bowden and welcome to the Geek Group. I'm here today with Santa Paul, because it's almost Christmas.
Yes, it is.
Okay, and we've just finished construction on our new 6-inch demo coil. There's really nothing special on this. It's just part of the new series of coils that we're building. But one of the problems that we've had forever, one of the hardest parts to get for coils, at least one of the most expensive, is top loads, a good toroidal top load. Because they're expensive, there aren't a lot of places that make them, and they're just generally a pain in the butt. Because they're delicate, we drop them.
Yeah.
We have one full of water, which
Really?
I think, yeah, because fire.
Fire.
Yeah.
It sloshes.
It sloshes, but I figure the water's on the inside, so it's not hurting anything. I got a plan to get it out, but I got to remember to do it.
Okay.
Because it's got a vent hole, that's how the water gets in.
Right.
So I want to put it on the roof on like a July day in full sun and just let it bake out. I just never remember to do it because it sits on the shelf.
Okay.
So you're going to see a lot of stuff in top loads, and today we're experimenting. We have, here, I'll grab it. This is the moment where I regret wearing a black shirt.
Dust.
We have, yeah, they're very dusty. We have this beautiful toroid. It's spun aluminum, welded halves. It's beautiful work. It's very nice.
30 by 9.
30 by 9 is this top
Yes.
load. And this is probably where we're going to end up.
Okay.
But because these are expensive and hard to get, I didn't want to use one on something as knucklehead as a little 6-inch coil. I want to save that for at least an 8. So we made this. Now this,
It's disconnected.
cool. This is a very high-tech system made of a pair of IKEA salad bowls, really. And Sam got together with the gang, this is day before yesterday, Saturday.
Yeah.
And just in a couple hours, made up some little aluminum tabs and did some really sexy work with copper rivets and joined together a pair of simple IKEA salad bowls, and we left one rivet long for a breakout point. And if you shake it, you can hear their button head rivets. So there's still a couple rattling around in
Very
it.
steampunk.
Yes, it's hardcore, it's cool. There's been a lot of Doctor Who references.
Yes.
So the problem is this one is so small that I think we don't have enough field control because we're really elevated up here. There's it's space wound, but there aren't a lot of windings up that high. And we're getting a lot of anger from the coil.
To put it bluntly.
Yeah. So what I'm going to do is put this on top. I'm not even going to bother actually connecting it because the wire's touching and it'll be fine. And we're going to fire this off here, and we're going to see what effect we get with this top load. And it's in tune, so we're cool there. Then we're going to put the other top load on, and we'll have the same power, the same capacitor, same everything. The only thing we're going to change is the tuning, and we'll see what difference we get just from going from a sphere to a toroid. Now the toroid's much larger, so we're gonna throw tuning all, yeah. But we can retune it in a couple minutes. That's no big deal. But it's what we're looking at is the effects it has here with because the top load affects the shape and the shielding of the electromagnetic field coming off of this. Because remember, everything here is electromagnetic. Like once we get to the primary, from there out, it's all just electromagnetics. And what's happening is our tank circuit down below is firing impulses of high voltage, high current electricity through this coil, through the primary coil, and that creates a pulsed electromagnetic field. Those pulses are striking it's kind of like a bell, where we smack the end of this with a big pulse, and this huge coil of wire gets, because you have a coil of wire inside an electromagnetic field, a changing electromagnetic field, you're going to induce a current in this wire. And that current rings. And it's all about tuning this to match a multiple of the resonant frequency of this, and it rings like a bell. The difference is, when you think of most things ringing, you think of like smacking a bell with a hammer. This is more resonant like how a violin works. We're putting in impulses in steps, and they're making the thing resonate up like that. That's how you get way more volts out than in. If this was just a straight transformer, we wouldn't get anywhere near the voltage rise that we're getting. We're doing this through what's called resonant rise, and that's the whole system. But because we have all this stuff happening with electromagnetic fields, the top load on top serves two functions. Most people just think of it as a capacitive load, and it is a capacitor, which is why it changes the tuning. But it's also controlling the shape of the electromagnetic field, especially in this area. A little bit down here, but especially in this area. And you want all that energy to go up and into the top load and then radiate out into the arc. You want to get all of the energy you possibly can from here, through here, out here. And if you don't, because standing waves and feedback and all kinds of stuff happening, you'll get racing arcs, which is where you have arcs going down the secondary coil. That's called racing arcs, where you'll get arcs down the side and they burn holes in it, and that's bad. Or you'll get primary strikes, which is where this can either come out and hit here, which is really bad, or come out from here, go down in a racing arc, and then jump out to here and hit the primary, which is really bad. You don't want to have anything here making an electrical connection to anything here. Now, when this is all done, it'll have what we call a strike rail. A strike rail is just an open loop of copper pipe that you don't want to have a full loop. You want to have a little gap in it, because if you have a full loop, you have a shorted turn and it'll suck huge amounts of energy out of the system. So you leave it open, just a 1 or 2 inch gap, and connect that directly to your RF ground, which comes off on this side here. This green wire is our RF ground. And you just dump that out safely. And that protects you. If you have a coil that's just prone to getting primary strikes, usually because your field shaping sucks, you just want it to come out and it's going to hit and it's going to try to hit the primary. You just put a primary and arc ring out here and it'll just hit that and it just dumps it out safe. So that's a thing that may happen with this coil. It all depends. So with that, you want to give it a shot?
Sure thing.
Let's do some stuff. All right, so we did a test.
Yeah.
Took it up to, and racing bad all over, and there's going to be some really pretty stills from that.
Yes.
And then we swapped out toroids, retuned, did another test. Racing arcs went away.
Mostly.
I had to crank it up to full power and hold it there for 30 seconds to do it. So that cured the racing arcs because now we have a totally differently shaped field.
Right.
And the output is the same or better.
Oh, much better.
And now we've replaced the test wire. Grab the lead we have there.
Here's the little stuff and here's the good stuff.
Okay. This is like 20 gauge. It's test lead wire. It's GTO cable. So it's really heavy duty silicone insulation, very thick. It's rated for, I think, 15 kilovolts.
Okay.
And this is really tiny wire. It's like 20 gauge. This is, I think, 12 gauge.
Looks like.
Yeah, it looks and feels like 12, and it's not actual GTO cable. It's something different, but it's rated for 15 kilovolts. It's got a hard outer jacket and a soft, gooey inner jacket, and there may or may not be some shielding in there. I don't think there is. It doesn't look like it. Okay.
There is not.
But this is much thicker cable. And in the tank circuit, down everything here, you want the thickest cables you can possibly get. It's important to have the insulation standoff, but thicker wire is better because the instantaneous current down in here is like 10,000 amps. It's really, really, really high current, so beefier wire is better. And when we do this for big coils, we don't even use wire. We go straight to using pipe at that point. And just by changing out the cables and getting everything shorter and compact from the lash up for the prototype stage, huge increase in performance.
Yes.
And all we did was change the wire. So here, all we've done is change the toroid and tuned it appropriately.
Yes.
Huge increase in performance. And now we've replaced that one last piece
Of the cheap stuff.
so we get to fire it up again and see how the performance is now with a better toroid and with that final piece out. So now it's all bigger wire and I expect this to perform admirably.
Then let's give it a shot.
All right, we're gonna test it again. All right, so we've done it. We have taken our spark output up to 63 inches right now, which is beautiful. And that's just slamming it. It's actually more than that, but it's, I'm not pushing my luck in this tiny little room.
Yeah.
But we can still drive this to racing arcs, but I firmly believe the reason why we can drive this to racing arcs is because we have a ridiculously oversized power supply on it right now.
Mr. Wysock's power supply. Isn't it?
And we're dumping it into it. Yeah, that's a original Bill Wysock power supply. And we're dumping this into a little 6-inch coil.
Yeah.
and I'm just grabbing that and I was like, how much will she take? Yeah! Crank it to 11, yeah! And then we get some racing arcs. And I just think we're overdriving this like crazy. But
Strike rail will help.
yeah.
Moving things out. A screw hole will
I'm
help.
not going to worry about that.
Not gonna worry about it?
This is done. This is finished. The only change I ever intend to make to this coil at all is putting a 10 kVA, maybe even smaller power supply in a little box that'll roll around with it.
Okay.
So that we can just power it right there, and I'd like to do that as a future project in 2017, which will make this, I want to get this off the Wysock supply because that's the lab testing supply. But until we build the 8-inch coil, which is next, it's sitting right there in progress. This is going to be the main demo coil for the Saturday tours.
Okay.
And I want this to be the main demo coil for exactly as long as until we can get the next one going. And after the 8, we step up to bipolar 12s, and that's where we're playing with big stuff. So today we got to talk about a little bit about tuning, a lot about field shaping, and how the effects of different size top loads can impact the performance of a Tesla coil. I want to thank everybody for watching and hanging out with me and Paul. You guys have fun, and as always, we'll see you next time.